So, happy Thanksgiving. Hope you guys had a good break. Hopefully, well rested and ready to finish off the semester. It's the first time I didn't travel for Thanksgiving I guess since moving away from where my family lives. So, been was pretty restful in that sense. Of course, miss my family, but extended family. All right, so today I want to come back to this problem that we left off on, work through that with you, talk about it, sort of show what's going on with it, and then go into kind of nutrient removal as a topic with kind of what we do with biosolids, how do we process them, and I might just show you some fun videos because we've got a few that we can look at with that. But we'll spend plenty of time on this problem first. Make sure everybody kind of has a good feel for how it works and what to do with it. So we'll start here. This part was essentially it's a two-part problem here, or example 5.7 in the book and example 5.8, as we see here. So we'll start with the 5.7 here. It says the wastewater in example 5.6. So previous problem, it has some information on it. And actually, before we even do that, just a quick reminder, last homework is due on Thursday. So that's been posted, that's there for you. Okay, so this problem is following some other one. I haven't bothered to go back to check exactly the characteristics of that particular water. Really, what it's probably going to tell us is what chloride concentration we expect in the water, and that tells us something about the dissolved oxygen, because dissolved oxygen relates to the saturation point relates to temperature and the presence of some species like chloride. And so for this problem, we'll just assume that we're at zero chloride because I don't have that information on hand. So when we look it up, it's going to be 20 degrees Celsius, and we'll see that's 9.09 milligrams per liter. Okay, so the dissolved oxygen concentration in the wastewater was 2 milligrams per liter, had a discharge rate of 1.1 cubic meters per second. River water receiving the waste had a dissolved oxygen equal to 8.3 milligrams per liter, flow rate of 8.7, and a temperature of 20 degrees Celsius. So assuming complete and instant mixing, we need to estimate the initial dissolved oxygen deficit of the mixture of the water and wastewater just downstream of the discharge point. So before we went to break, I kind of ended on this slide and said, well, here's the deal. It's kind of a mass balance. We need to solve for the dissolved oxygen and then use that to find the deficit. So take a couple minutes and do that. Get your mind's working, and then we'll take a look at the kind of the more in-depth portion after that. All right. So you see, I have most of the solution up so far. Just basically combining the two streams, but we need to do it. We're solving for the deficit, um, and so that could get a little tricky. We don't really want to treat the deficit as a discrete thing, um, especially if it were the case that the wastewater had a different composition or temperature than the river. Then we really don't want to treat it as a discrete thing, because what we're really talking about is how much oxygen is there. And then with the mixture, how much is missing that, out of the total that could be there. So the best way to do this would be to do it on the basis of dissolved oxygen and then convert to deficit afterwards, right? So we're going to go ahead and solve this for the dissolved oxygen of the mixture. We can do that. That's 7.59 milligrams per liter is present in the mixture downriver. And so then the deficit of the mixture, we could also call as the initial deficit for the problem, D naught, is going to be the dissolved oxygen at saturation minus the dissolved oxygen of the mixture. So that's going to be 9.09 minus 7.59 should give us 1.5 milligrams per liter deficit. Okay, Make sense? All right. Okay, so then the next problem, 5.8, we say just below this point, we have that discharge. The BOD is 10.9 milligrams per liter. The DO is 7.6, like we just solved, milligrams per liter. The river water, the river and waste mixture has a temperature of 20 degrees Celsius, a deoxygenation constant KD of 0.2 per day, an average flow speed of 0.3 meters per second, and an average depth of 3 meters. So in other words, it's just a continuation. All right, and then this problem says A, find the time and distance downstream at which the oxygen deficit is at a maximum, and B, find the minimum value of dissolved oxygen that occurs for this system. So I've got the equations we went over last time here. So take a few minutes, work on that. I will join you in a couple minutes to help kind of guide you along. But give that a few minutes, see how you feel about it. Sorry. This is from last problem. It's the speed, not flow rate.
Look, my struggle here is variables. That's one of the things we don't know. So your KR value would be 0.4, give or take, inversely. What that lets us go to, we have D not, we have B, we have KD, we don't have T. We need something with one or the other variable. Is this one of those where we find everything? Can't do that. Couldn't TC be? Yeah, we go down the bottom. No, we don't. Pretty sure it's just a regular flow. Might go to the next one. Let's at least put it. We have our D. That's what I was thinking, but I want to see. Yeah. I kind of want to just find what we have in here and see what we get first.
All right, so just real quick, you can see I solved for KR for the problem. We're taking D initial as the thing we solved for last time. The initial deficit is 1.5 milligrams per liter. KR, we have this formula. This is the speed. U is the speed of the river. H is the height, the average depth. So we can put that in. This is a weird one. If you were trying to follow the units, good for you, but this is just a strange situation where this would be like meters to the 1/2 over seconds to the 1/2. That all divided by meters to the 3/2. So like you might be able to get seconds to the 1/2 on the denominator, but that's none of that actually matters, because what we were told from the book is that this is an empirically derived way to get to a rate constant in per day units based on measuring the river speed and depth in meters and seconds. Okay, so normally I tell you units are everything. This is an empirically derived situation, so we're just going to say magic 0.411 per day. And that is, by the way, within the range. We said a waterfall is like 1 or more per day. A slow stagnant pond would be like 0.1. Okay, so we've got that. We also notice that this is not equal to KD. and that's good. That means we don't use this equation, right? Because we are allowed to do Kr minus Kd so long as they're not equal to each other. All right, so let's finish up part A here. So at this point, the only pieces of information remaining, because we have, if we take a look at the equation we're going to need here, it's the time for the critical. This is going to give us a solution to part A because we're looking at that time. We can take that to distance using the velocity of the river. That means that for the dissolved oxygen at the minimum dissolved oxygen, we can use this equation here, which is the deficit at some given time, T, and we can plug that in and use that there. So for this case, we need this equation. We've got Kr because we solved it. We were given Kd. So what remains is the dissolved oxygen initial, which we were given, or well, we solved last time, and L naught. So L naught can be complicated by some calculations. What we're given though is basically what we need. So it says the pollution mixes with a river. The BOD is 10.9 milligrams per liter just after that mixing. And so it doesn't say the BOD 5 was measured. It doesn't say, it doesn't give us much information aside from the BOD is. And so I'm taking that to mean that L naught, because L naught is the ultimate amount of BOD if you were to let it go forever. And so they weren't specifying they did a 5-day test or anything. So I'm going to take that to be 10.9 milligrams per liter. Now, just a quick side note. If we take a look at our formula sheet, we can we might notice that we have this BOD equation. We also have this guy here, which is what we might use to solve for L naught if we know something about the BOD at time t, and we have some rate constant for the BOD consumption rate. And we're not given either of those. This is just, we're just given the BOD is there. That's it. That's what it is at this starting point. So because that's the starting point, that's what I'm saying, okay, I think that's just L naught. Okay, so that certainly understand if you were trying to make something more of that, but I think that's where we have to go. So with that, then we can take an Excel sheet, put in the numbers, and solve essentially. Oops. So we have L naught here, all these parameters. So I went ahead and put it in and just followed the formula here. Let's see if I can show it a little better. So we had the 1 over KR minus KD times the natural log of KR over KD times 1 minus D naught KR minus KD divided by KD times L naught. So assuming I got that all in here correctly, which I think I did, that should come out to be 2.67 days. So the critical time for this scenario is just over 2.5 days after the discharge, which kind of tells you something about how, what kind of impact you could be having and not even know it, right? So then we can convert and say the speed times the time should give us the distance for that critical point, and that, let's do real quick. We'll call it XC. That was 0.3 meters per second. And that's in seconds, but our time is in days, so we probably should convert. So that'll be times 86,400. That's going to give us meters, but that's going to be a large number. So I'm going to go ahead and divide by 1,000 to get to kilometers. So that's 69.2 kilometers. So nearly 70 kilometers, 30, 40 miles, however that converts. So you can really see how that could be a big impact to the water quite far away. Given these conditions. All right, so that's part A. Part B is more calculator entry, essentially. So here we need to find the minimum value of DO. So we need to find the maximum deficit. Maximum deficit is going to be at this critical point. So we're essentially going to solve for D equals all this stuff at T equal to 2.67 days. Okay, so that's the deal here. And again, we can come back to Excel. And I've done something wrong. I did it just fine this morning, but this time I've punched something in wrong. So see if we can find that and get our answer here. So deficit should be equal to the KD times L naught. KD, actually what I'll do is I'll just do it again. You can catch me if you see what I do wrong. So we need KD times L naught divided by KR minus KD times the natural log, times this stuff, times exponent, so e to the minus KD times time. Got the time here. Minus e to the minus kr times time. And I'm going to close that entire section. Add d naught times e to the minus kr times time. Okay, yeah, that should not be.
I wish it would like what they're changing.
Yeah, I'm just gonna say yes and see how that goes. Okay.
The only thing I could think of would be separating what you're dividing from everything else. Because if you're reading it left to right, it looks like you're dividing by a very large number because you're just multiplying everything else, right?
Yeah, so it usually works okay. So I have this amount. So this times this divided by this times this. Usually works out.
Yeah.
I mean, we can add more parentheses. It won't hurt anything.
That's the only thing I could have thought of.
Yeah, but this is a. I don't think that's the answer I got earlier today. So I'm slightly concerned. But so that would be the deficit, which would mean the dissolved oxygen at minimum would be 9.09 minus that deficit, right? Because that's the saturation value minus the deficit should give us the amount. Definitely different than what I had earlier today. Maybe I flipped some sort of a. This is KR minus KD. And then we do KD minus KR. Okay. So perhaps I did it wrong earlier and it was just slightly off. At any rate, if you enter everything in correctly, you'll get an answer. This is a reasonable answer, right? It's within the bounds of our saturation value and 0, so that's good. Unlike the first time I punched it in here. So you can certainly double check that, see what you get. I'm going to go ahead and write this down as 5.98. Well, so actually we'll say D first of all was 3.1. Meaning the DO minimum was 5.98. Okay, so not a huge impact. Given those conditions. All right, does that make sense? Okay with that?
Oh, that's
Yeah, 9.09 again was coming from the saturation value that we could look up from that table here. And that might be maybe the previous problem, 5.6 or whatever, gave us some chloride concentration to work with. So we could have done that a bit different, but that's okay. All right, so that'll be it for the BOD dissolved oxygen kind of stuff. So next, we'll talk about nutrients. So specifically, I mean, we talk about BOD, mostly what we're referring to is that biological oxygen demand, probably carbon-based stuff. And so when we think of it in that term, if we add a bunch of like sugar, it's mostly carbon, bacteria will eat it. and they'll deprive the water column of oxygen. So that's a problem, but we can also run into a problem even if we don't feed them the carbonaceous food source. If we give them plenty of nutrients, that still could trigger some algal blooms or just microbial population booms if either there's already some material for them to consume as an energy source in place, or in the case of algae and cyanobacteria, they're just going to take it from the atmosphere. They'll take the carbon they need, they'll do photosynthesis, and now they have plenty of nitrogen and phosphorus to deal with. So what they'll do is create this, vibrant orange color you'll see in some ponds occasionally, and this is what we call eutrophication. Which essentially means that we've got so much bacteria, so much algae, so much cyanobacteria, all that growing, that it's going to crowd out the sun, so the sun can't get deep into the water column. So then you have up at the top, during the day, a lot of algae producing oxygen. But as soon as you go below the space where the sun can shine, everything's doing respiration and just consuming the dead algae cells and things. So you've got essentially a creation of BOD underneath that blanket. And as soon as the sun turns off for the night, what you'll have is all of the algae and all the bacteria are going to be doing respiration instead of photosynthesis, right? So then you're having consumption of oxygen for all that. So then you have an oxygen deprivation situation. You get fish kills and all of that, all the bad stuff we were trying to avoid by not discharging BOD directly in the first place. So BOD then is not the full story. If we have a bunch of nitrogen or phosphorus, we could have some serious problems. And you'll see this pretty frequently with agriculture runoff. If you see a pond that's on some sort of a agriculture farmland type of thing, chances are they sometimes will have algae blooms, just given the situation of that local environment. Okay, so to understand a little bit how we remove them, I'm going to first comment on aquarium. So aquaria, I guess, or aquarium. Is it aquariums or aquaria? I think it's aquaria. So fancy, okay. So if I'm torn about being fancy, I just call plural aquarium. I'm like, oops. All right. So if you've ever, how many of you have owned an aquarium at any point? All right. So as a kid, I ended up having two in my bedroom, and that's kind of like one of the things that really connected me and inspired me to do water treatment kind of stuff. So I always loved the aquaria, having the aquariums. I don't know, whatever. I'm not fancy. Having them, and what I would do is I would just kind of play in the creek behind my house and catch whatever I could find and see if I can keep it alive and all that, right? So that was sort of my inspiration for water quality, water treatment stuff. And if you've ever started up a new aquarium, one thing you probably noticed is after about a week, maybe 10 days, your fish died. First time you tried it, right? So then it's a matter of, are you disappointed and never try again? Or are you persistent and go buy some more goldfish or whatever and try one more time, see if you can do it right. And so this little bit here is kind of going to explain that. So the nutrient, the nitrogen in particular, nitrogen cycle, is quite important because ammonia is toxic to aquatic life at pretty low levels. So if you've got 0.5 milligram per liter or more, you're starting to get in a range where you've got some significant toxicity. So what happens in a brand new aquarium? There's not really a whole lot of bacteria around. You've got oxygenation, all this happening, and you put a fish in there and you're excited and it's like you're trying to make sure it's happy, so you give it a lot of food. Well, it's going to start excreting some nitrogen in the form of urea, and that quickly becomes ammonia, which builds up in the system. So if you've got some sort of a nitrogen input for food, and then, nothing else no bacteria is taking care of it. If this is your ammonia / ammonium, your fish is in danger, right? It's not going to be a good day. So what we want, or what happens in nature, and when we have established nitrifying bacteria and all the ones that can process it, is it'll convert the ammonia, NH3, NH4, to nitrite first. Nitrite is a little bit toxic itself, so that could be a problem, and then ultimately goes to nitrate. And these are bacteria that are doing that task. So when you have brand new, fresh, sterile pebbles and everything, and the walls of your aquarium are super clean, there's just no bacteria to do that. So you just get a buildup of toxic ammonia, and then your fish die. But a few weeks later, there's been enough stuff in there that the bacteria are starting to grow, start colonizing all the little pebbles, rocks, and walls and things. And so the next time, unless you bleached the whole system or something, next time you try, the fish will probably survive. Also, speaking of aquaria, okay, now I'm fancy. A hungry fish is a happy fish, so don't overfeed. It's always safer to just let it be a little bit hungry. I right now I have a little. I think it's a long-eared sunfish I caught in the co-meet. Beautiful fish, and when I traveled for research for a couple weeks over the summer, I just fed it well beforehand and just let it sit there for 2 weeks. It was fine. Came back, he was happy, right? So happy fish is a hungry fish that just won't grow as fast. So anyhow, what happens in nature then, when we do have the population, is we'll have maybe some source of ammonia, but it'll quickly be converted. So if we've got kind of a continuous source, or we're inputting into downstream, maybe this is like wastewater, right? And we've got organic ammonia or organic nitrogen that is breaking down and becoming ammonia, and some ammonia right away. It might look something like this, where that's our NH3 or NH4 plus. So then that will relatively quickly start converting into nitrite if we've got the bacteria present. So we might not start with much nitrite, but then we'll have something like that. And then the nitrite, NO2- starts converting into nitrate. And nitrate is sort of the safer, more stable one. And in fact, actually, will probably be remaining mostly as that. So maybe it'll look something along those lines. Eventually, some bacteria could take nitrate into nitrogen gas. That's a particular scenario, and you usually have to have anoxic conditions. Okay, so that's kind of the deal. And so now you know how to start up an aquarium better. Next time, you could even take a little bit of household ammonia, or some other source of organic rich. It's basically like the fish's urine. So any type will do if you just add a little in there, something like that, of that nature, and let it sit there for a couple weeks. Maybe take some natural rocks from the stream nearby or something, add them in there so that there's some bacteria to kickstart it. If you're going to be real fancy and buying the expensive fish and things, maybe you don't want to do that because you don't want to get it sick or whatever. So there's people that are kind of crazy about it. Okay, so nitrogen cycle, we kind of did just talk about that. And if you are more interested in nitrogen cycle management in particular, at the end I've got 3 links. Here's one of the videos. It's got cute little microbe dudes that it will show you. I'll just play it for a moment. You can get a feel for it. Come back to it if you'd like.
Much like carbon, nitrogen follows a basic pathway in a continuous cycle. This cycle is critical to all living organisms that have existed or will exist on the planet.
Like
Wastewater
it's catching the
treatment plants
algae,
play
or
a
it's
critical role in reintroducing nitrogen back into this cycle with limited environmental impact. High levels of nitrogen entering natural waterways can
I haven't done a saltwater aquarium. Yeah, so the algae are going to do. They're essentially going to be like some microbes will convert from ammonia to that. That'll be the nitrifying bacteria. Algae will probably just take it straight up and consume it to make new cells. So that would certainly be one way to do it. And there you go. Yeah. And so that's, kind of tying it back in. That's essentially what we're talking about right here. So Luke was just saying that they use an algae filter. You're essentially doing assimilation where you can also take from ammonia directly to assimilate. Plants and algae will just take it directly as a nitrogen source, like fertilizer, right? That's why we add fertilizer. And then you just have extra algae in that case, or your plants are growing, and then you can take them, do whatever you need to, but it's taken the ammonia out of the system. So we talked about this a little before, and we call it nitrification, going from ammonia to like these nitrite, nitrate, denitrification, going back to ammonia gas, or excuse me, nitrogen gas. All right, so nitrogen removal processes, like kind of in practice, in a way we often think of them as kind of like a tertiary treatment step, because we've got that primary and secondary, and then anything else we add that's going to be fancy is sort of tertiary. But we can also put it directly in line or in step with the secondary treatment process. So here is one example. We've got sequential carbon oxidation. Carbon oxidation, that's kind of the typical waste activated sludge aeration basin that we've talked about. But adding nitrification, denitrification to it. So we've got our typical primary sedimentation, that primary treatment, sending it along. And then here we have combined carbon oxidation, nitrification. So what we're talking about is they're taking as much ammonia as possible and sending it over to nitrite and nitrate. That's an oxidation process, adding oxygen to help that happen. And then we have this anoxic denitrification, where we're going to remove the oxygen intentionally so that the bacteria that are around can use the oxygens attached to the nitrate as an oxygen source. And so then they're going to continue. It's a different type of bacteria typically, so you have to set up the conditions nicely for it. But then you're getting this nitrogen gas, which is basically pretty much inert and takes a lot of energy to convert that back into like a usable form. So once we convert it there, it's pretty much removed. So then after that, you can do the secondary sedimentation and carry about your merry way. Another type, and this one gets a bit more phosphorus. This is the Bardenfo system. It's kind of the same thing, except it's a little bit reversed, and it's sequenced another couple of times. And so we see that the return sludge is carefully done so that we're doing it after aerobic here. So we start with anoxic. So we start off by trying to go whatever nitrate and nitrite we have. We get that N2 gas, but there's going to be a lot of ammonia. In fact, this process is probably going to help break down some of the organics into ammonia. So then we have the typical aerobic chamber where then we've got NH3 going to more nitrate, followed by another sequence where we're going to do the same thing and ending with an aerobic tank. And that's probably preferable anyway. If you're going to discharge wastewater, you probably want it to be as full of oxygen as you can to avoid this whole BOD problem in the first place, right? So it's kind of a sequenced sort of a situation, a little bit more advanced in terms of the biochemistry and some of that management, but that would be a common way to do it. The phosphorus cycle is a lot different than the nitrogen cycle because it has no atmospheric component unless you're counting bird bombs. So birds actually do export a lot of phosphorus from what they eat into wherever they're excreting their waste. And so there are like bird islands near like ocean areas, sometimes it can accumulate lots and lots of phosphorus because their excrement happens to be quite phosphorus rich. Bat guano as well, is part of the reason why it was used to make explosives early on. But aside from that, it's pretty much mineral deposits and aqueous marine systems. So that's tends to be either a mineral or some sort of phosphate compound, and then in biological systems, there's a little bit of it in pretty much every living cell. So if you remember from biology, we have what's called phospholipid membranes, kind of help control cell membranes and different other membranes within our biological system. So it's essential for biology. In that sense, it's like a macronutrient. But also, if you remember, we talked about that CNP ratio. I think I've got it somewhere. That CNP ratio, we had like 100 times more carbon, something like than the phosphorus, and about 15 times the nitrogen as we had phosphorus. It's like 100 to 15 to 1 or thereabouts. So that CNP ratio kind of shows us we need phosphorus, macronutrient, but it's the smallest of them. Okay, there's a few different designs we could go into, the anaerobic, anoxic, just kind of different ways to specifically target phosphorus removal. Sometimes you might add the other nutrients to make sure phosphorus is limiting, something like that. But I'm going to move on from that. Actually, that's a good moment. We have another video here. This is basically an advertisement, an instructional one for some company that thinks their little mixer aerator thing is really, really fancy for wastewater ponds. So I'll let this play. It's basically like 3 or 4 minutes, and we'll see what they have to say.
Educational whiteboard series, Everything Wastewater, produced for engineers, system owners, management, and personnel to answer commonly asked questions about wastewater applications and Medora Corporation equipment. How can Medora's floating wastewater mixing equipment be used to meet phosphorus limits in a wastewater lagoon? In the next 3 minutes or so, we'll explain the basic process and equipment needed to achieve the best, most economical, and easiest phosphorus removal in the industry. Where to start? Let's dig into some quick phosphorus fundamentals. Phosphorus is an abundant, naturally occurring element essential to all life on Earth. Excessive phosphorus in waterways and water bodies can cause environmental complications such as dense plant, algae, and cyanobacteria growth known as eutrophication. By removing phosphorus during the wastewater treatment process, there are less potential downstream negative impacts. Less phosphorus release, less negative environmental impact. And as time moves on, phosphorus discharge limits for lagoons will only become more strict, increasing the urgency for a reliable and effective phosphorus removal strategy. So let's get our removal on. Phosphorus can be removed from a lagoon by applying a precipitating agent like aluminum sulfate or ferric chloride. Once precipitated, the phosphorus harmlessly falls out of the water column and into the sludge sediments. Precipitant dispersal is a very hands-on and costly process requiring extensive labor, time, infrastructure, and accessory resources. In short, it can be spendy. This is where Medora's floating wastewater mixing equipment can make phosphorus removal a whole lot easier and more cost-effective. And it all starts with a floating wastewater mixer. The mixer is anchored using a single shore-to-shore tethered cable which is able to span most lagoon dimensions. Once tethered, an injection hose is run from shore to the machine fastened along the tether cable, terminating just below the machine impeller. And just like that, Medora's floating wastewater mixer is now ready to receive and distribute the phosphorus precipitant of your choice. Consult with your chemical supplier for proper sizing of metering pumps, chemical storage, and dosing rates for your lagoon. Then, all is left is the final connection to the mixer injection hose, and you're ready to rock. The phosphorus precipitating agent is sent from the onshore metering system down the injection hose to the machine just below the impeller. Here, the precipitating agent is fully mixed into the entire direct flow of the floating wastewater mixer. And this is where great mixing takes center stage. The well-mixed precipitant is then distributed radially across the lagoon utilizing proven long-distance circulation technology. It creates an ideal interaction environment between your precipitating agent and the target phosphorus. In many cases, when compared to traditional application methods, only half as much precipitant is needed to achieve better phosphorus removal, or simply put, the better the mixing, the better the phosphorus precipitation. And Medora wastewater mixing is the best there is. Even better yet, Medora Corporation has effective mixing options no matter your lagoon size. 1 acre, 15 acres, more, less, in between, doesn't matter. Medora Corporation has you covered. Medora floating wastewater.
All right, so you never knew that mixers could be so fancy, right? Are you all going to go buy one for your wastewater lagoon now? So it's kind of funny that there's enough audience for such products that you make such a dramatic attempt such a persuasive advertisement for it. Okay, but it's is also instructional, so I appreciate that. Okay, so moving on from that, one of the concepts we've mentioned a couple times is what do we do with all the junk that we collect, the sludge we produce, all these bacteria and everything, and essentially we call them biosolids if we are going to recycle them. So we take them, we have some safety concerns, pathogen reduction as a must, contaminant containment, and then obviously if they're not properly treated or composted, then we have serious concerns about handling and all of that. But what we can use them for, potentially, this is why we are interested, is adding fertilizer. And that would be adding the nitrogen, phosphorus, and there'd also be plenty of potassium. Adding directly to soil, and in a sense, we would be closing this loop of in agriculture, we want to take nitrogen from the atmosphere, make it bioavailable, so that we can grow plants. Right? That's effectively what we're doing. In wastewater, now that we have all this organic matter, we're trying to not discharge that out into nature because of the problems it would cause. So if we could just take it there, rather than, perform the oxidation required and all the energy you spent for that to send it back, the nitrogen in particular, back to the atmosphere, and then, separately the fertilizer producers are going to take the nitrogen from the atmosphere, send it through the energy-intensive process to get it into an ammonia or nitrate form for application. If we could just skip all that, we would save a lot of energy, right? A much more sustainable and economical thing to do. So that would be good. It would also give us a better way to dispose of the wastes rather than just filling up landfills. And we can also potentially recover biogas during the production of these biosolids. Okay, so some good, compelling reasons to do so. I'm going to rush through a few and maybe just let you watch the last video, which is kind of on biogas production from essentially manure processing. Okay, so biosolids, lots of, it's going to be a little bit like making topsoil out of wastewater solids. So it'll end up being applied something like this, or perhaps sprayed over land. A lot of benefits, potentially. Fertilizer, potentially improve soil quality in terms of airability, how well it holds water, also how well it drains water if you have like clay type soils. So all the things you'd get with adding some sort of humus topsoil type of stuff. So potential benefits, some obvious disadvantages: odor, especially at the production site. You've got this anaerobic process happening, partially anaerobic. So it's going to be kind of stinky. If you have primary pathogens survive, that's a big problem. And then there's also potential to disperse secondary pathogens, aspergillus. I think that's a fungi, some other particulate matter, other airborne allergens. So there's definitely some concerns, and I know there's some worker safety issues with the people that are applying the biosolids, especially the class B, which are not as strictly cleaned. Definitely some considerations there for health. You also have some potential for lack of consistency in the product that you make. It kind of depends on what's happening with the wastewater system. Okay, so there's two classes of biosolids, A and B. A is the fancy stuff. Essentially, there's a couple of different methods to create them. One would be what we call an aerated static pile, or likewise an aerated in-vessel system. And the requirements there are that you have to achieve 55 degrees Celsius internal temperature for at least 3 days. As a reference, body temperature, human body temperature is 37 degrees Celsius. So this is up, 130, 140 degrees Fahrenheit, something like that, nearing some of our food safe metrics, right? So it's hot. It's not like burning. Maybe it's 120. So maybe it's not quite that, but it certainly will kill a lot of pathogens. I work with E. coli sometimes, like a non-pathogenic variety in my lab, and I know that if we touch it to a 50 degrees Celsius liquid as part of a process, they die pretty quick. We have to keep it down to like 45 degrees Celsius. So something like E. coli would not stand a chance. There are some thermal resistant bacteria, and there's going to be plenty of microbes that are existing and thriving at this point. And it's actually that biological activity and some just chemistry that's happening that's elevating the heat in the first place. So we're not adding heat here. This is all just exogenous heat coming from the processes there. In fact, if you aren't careful and you let it get away from you, you can have fires, which are pretty crazy and dangerous, like landfill fires. If you get a fire burning underground, it's going to rage, or it's going to go wild as soon as it has oxygen. So, those are crazy things. Okay, so there's another method where you have, I think it's just like a vat of it, and you have to turn it a few times. That's your oxygen addition, and that says you have to have 55 Celsius for at least 15 days with 5 turnovers. The class B then is a 40 degrees Celsius or higher for 5 days, during which temperature exceeded 55 degrees for at least 4 hours. So you have to hit that mark, but it's just generally more relaxed. Okay, so those are the two classes. Not a big difference there. It's basically just fancy composting, carefully controlled. We have all sorts of regulations about the metals and as pollutants. This is actually under the NPDES system. Most states have, I think Louisiana is one of them. A lot of states have biosolids programs. If they don't, then the EPA handles this. But the state DEQ probably, I think LADEQ or LDQ has it. And so basically there's limits on how much can be applied to the land at a lifetime total and how much that can exist in your actual biosolids. So there's a couple different things there because we don't want to be filling our land with heavy metals. Okay, so typical steps to do all this is to, first of all, dewater the sludge, and sometimes you bulk it with something like sawdust, rice hulls, coconut husk, something just that's organic. It's probably wanted to throw it away anyway, but it helps keep this muddy sludge stuff a little bit more aerated. So you dewater to a point. You have to still have about 50% water by mass, I think. And your target is to reach 55, somewhere between 55 and 65 Celsius. It's pathogen control, and it's also going to help with evaporation. After you do the process, you let it stabilize. Might need a little extra drying, and then in some cases maybe you'll remove the bulking agent again. But I think usually you just leave it. It's probably something, like I said, you wanted to dispose of anyway. So a few metrics here. For organic matter decomposition, you really need a bare minimum like 12 to 15% water moisture content for any activity to occur. Anything less than 40% is probably going to slow it down a bit. So usually 50 to 60. And if you get upwards of 60% moisture, you're starting to turn it all into mud. So you have to dewater from there. Okay, this is what it looks like for that aerated static pile, where you are pulling air in through some sort of a covering blanket sort of thing through the sludge, and then you have some sort of filter to capture as much odor and stuff as you can on its way out. You could also be capturing in the system methane that's produced during these organic decomposition processes. I'll play a little bit of that other video here in a moment. Talk more about that. So there's all sorts of in-vessel designs we could look at. That's what the video will show. And here are the links for those videos. So I'm going to let this last one play for a little bit. Probably won't go quite through the whole thing. Again, it's a little bit of an advertisement, not the best production quality, but it's interesting.
Welcome to a virtual tour through one of BioConstruct's biogas plants. Controlled fermentation of biomass in biogas plants produces a gas that can be used to produce electric or thermal energy on account of its high percentage of methane. The raw materials used in biogas plants, also known as substrates, are often liquid manure, agricultural products, and agro-industrial waste. The following animation will demonstrate how electricity and heat are produced from these substrates in biogas plants made by BioConstruct. This biogas plant uses ensilaged maize as one of its renewable raw materials. With the aid of a wheel loader, the maize is tipped into a cement storage bin, which needs filling up approximately once a day. Silo maize is rich in energy, and on account of its high degree of reduction, very well suited for use in biogas plants. This storage bin is equipped with a hydraulic floor discharger that continuously feeds the maize onto a conveyor belt. A scale under the conveyor belt registers the weight of the maize silage. Liquid manure is the most important basic substrate used in this biogas plant. After a short interim storage in the pigsties, it is pumped through pipes directly into the blending pump beside the maize conveyor belt. At the same time, the maize falls off the conveyor belt into this apparatus, which is equipped with 2 mixing rollers. In this way, the maize silage is mixed before fermentation.
The corn then is kind of bulking, and I think it's just corn husks probably. Found it. What? Look, they're calling it maize.
Yeah.
With this technology, it is possible to supply several fermentation tanks, also known as fermenters, with fresh substrates, even if they are not close together. Liquid waste from the food industry is the third substrate used in this plant. As the availability of such waste varies considerably, a large storage pit should be installed. Integrating this into a hall serves to minimize smells and to help prevent epidemics. Now the liquid waste is heated with hot water to 70 degrees centigrade in a tubular heat exchanger using a countercurrent process. After heating for 1 hour, the hydrogenization of the substrates is complete, so that they can now also be poured into the fermenters.
So obviously this is the fancy version of compost here, adding heat
The
themselves.
substrates are continuously stirred in order to prevent layers of material forming at the top or on the bottom. A hot water wall heater heats the substrate to between 35 and 55 degrees centigrade in order to accelerate the formation of methane. On average, the substrate is in the fermenter for a period of around 30 days, before it is filled into another fermenter for a further 30 days to complete the gas formation process. When fermentation is complete, the thin liquid substrate is pumped into 2 reinforced concrete tanks, where it is stored until it can be brought out onto the fields. fermenters are filled regularly with biomass, are airtight, heated, and regularly stirred. The biogas forms within a matter of days. The formation of gas is a complex and delicate process. The organic fats or carbohydrates contained in the substrates are digested by various kinds of bacteria, and this is a starting point for the development of the gas. If the contents are continually stirred, the gas rises slowly to the top of the container. It consists
Cute
of
little
approximately
microbes.
50 to 70% methane, colored green here, and also carbon dioxide, water vapor, hydrogen, and hydrogen sulfide. As water vapor and hydrogen sulfide are problematic for the utilization of the gas later, it is necessary to treat the biogas now. The gas is first freed from water vapor, colored blue here. The condensation water is collected in a condensation shaft and pumped out. The aggressive trace gas hydrogen sulfide is now extracted from the biogas in a biological desulfurization plant. By introducing air into the container, certain bacteria cultures are able to establish colonies on the chain. Here they decompose hydrogen sulfide into harmless sulfur and water. The almost unpressurized biogas is then fed into a compressor, where it is brought up to the 70 millibar pressure later required for burning. In order to completely condense any remaining water vapor and to free the biogas from any suspended matter or silicates, the biogas is subjected to a washing and drying process. This is carried out with the vapor at almost freezing point so that the gas is cooled down to a temperature of under 5 degrees centigrade. In order to control the purification of the gas, the biogas is constantly tested with an online measuring system, which records the amounts of methane, hydrogen sulfide, carbon dioxide, and oxygen. This guarantees a high degree of efficiency and security. In case of any overproduction of biogas, it is necessary to operate a gas flare, for unburned methane that escapes into the atmosphere is harmful for the climate. The biogas from this biogas plant enables two-block heating and generating power stations to run and be CO2 neutral. To annually process biogas from 15,000 tons of biomass, this plant must produce a total of 500 kilowatts of electricity.
Just trying to give you
For the
epilepsy.
optimal gas processing, the engines can run round the clock for several years with only a minimum of maintenance costs. Up to 30% of the waste heat from the cooling water of the engines is used for the heat exchange and the fermenter, so that no additional heat is required. The remaining heat can also be used profitably to heat industrial plants, houses, or swimming pools. The electric power generated by the generator of the block heating and generating plant is converted to the mains voltage level in the transformer. Then the electricity can be fed into the grid and meets the annual requirements of around 1,000 households.
All right. So it's kind of neat. Figured I'd show you that as like the very fanciest compost, what to do with your wastewater. And there, like I said earlier, it's kind of agriculture, essentially taking manure and then corn husks or something like that as their substrate, doing all that fancy stuff, and it's producing enough methane to power all of the operations and then some. Right, so it's pretty neat, doing a lot of functions there. Okay, so that's all I've got for you. On Thursday, we'll go over the last homework and any other questions you've got for the exam. And I don't know. So you'll have 2 hours. It'll probably be a lot like a normal exam. You can probably expect like maybe one more question on it because we are doing sort of comprehensive.
The exam is not true cumulative, it's just everything. I mean, technically it's cumulative, right? Because it's the stuff that we knew before to get here.
Yeah.
But, like, is it more or less on what we just...
Well, the way I'll describe it, and I'll talk more about it on Thursday, is that about half of it will feel like the cumulative aspect, and half of it will be like the stuff we just did.
The new.
Yeah.
Other stuff.